Hi everyone, this is the preview lecture for lecture number 4. In the previous lecture, we have introduced the Laplace equation, and for simple 1D cases, we have solved Laplace equation. It was not that difficult. After that, at the end of our previous lecture, we have introduced the Poisson equation. So if we have source-free case, what does it mean? If we have this kind of Poisson equation, then when we have source equal to 0 at everywhere, then it becomes just a Laplacian equation. If this is really the Poisson equation, then if we introduce source-free condition, then we can get Laplace equation. However, please note that our equation itself is not exactly in the form of a Poisson equation. If we write down once again, it has the form like this. Our unknown function f is first took in the gradient operator, and position dependent component coefficient epsilon is multiplied. After that we take the divergence, then it becomes minus rho, where rho is the net charge density. So think about once again the source-free condition. So here when we say source-free condition, it means that we have no net charge density everywhere in our system. So rho equal to 0 at every position, our charge is perfectly balanced. Then what will happen? Eventually we will have something like this: epsilon gradient phi equal to 0. So can we call it as Laplace equation? Of course it is not. Therefore our solution method for this source-free Poisson equation should be different from that for the Laplace equation. In the lecture 4, we will study the way to solve the Poisson equation. Somebody can ask me a question: why do we bother about the Poisson equation, the generalized Poisson equation? Can we cast our problem into the ordinary Poisson equation? The answer is not that simple, because we have different permittivity for different materials. Therefore, this position dependent epsilon cannot be neglected in our consideration. So that's the reason why we have to stick with this form of the Gauss law. Okay, so then let's go to the next slide. Here we have the Laplace equation. This is the Laplace equation in 1D case, and when we introduce the source-free condition to our generalized Poisson equation, simply Poisson equation, then we will have this form. When we make a comparison between them, we can easily recognize that this position dependent term introduce big difference in the Poisson equation. So how can you treat it? We have one example. So where the Laplace equation is applied and source-free Poisson equation is applied. There are two different samples. These and that are dielectric samples, and we have the same domain for our two different structures. So starting from x equal to 0, ending at x equal to a. Also starting from x equal 0 and ending at x equal to a. Also at the end of these two samples, we have so-called contact. Okay, so here we have applied 0 volt to the left contact and 1 volt to right contact. So also in the right sample, we have applied 0 volt to x equal to 0 and 1 volt at x equal to a. Up to now, everything looks quite identical. Left sample, right sample have the same length and same bias condition. However, the difference between them is now discussed. Between these two contacts, we have dielectric material, and in the left sample, we have just homogeneous material. Silicon's relative permittivity is usually said 11.7. So we have just silicon, and we have no carrier at all, no charge inside this system. And what will happen to our electric field when we apply 1 volt difference between this contact and that contact? That can be answered by our Laplace equation. Why the Laplace equation is enough? In this case, since epsilon is just 11.7 epsilon naught, so this is really position independent. Our equation dx epsilon d phi dx equal to minus epsilon can be easily written in the following form. Second order derivative of phi equal to minus times rho and 11.7 epsilon naught, which is corresponding to the epsilon in the left sample. Everything is quite simple and clear. But let's think about the right sample. In this case, we have two different materials. In this left half of the right sample, we have the relative permittivity corresponding to 11.7. This is just silicon. Once again, half of it is made of silicon. And how about the remaining half? In this case, we have relative permittivity of 3.9. What is it? This is corresponding to silicon dioxide. So now we have a sample. Half of it is made of silicon and half of it is made of silicon dioxide. Then what will happen to this sample? If we consider this form again, then we can say when we have the regions like larger than 0 and smaller than half of a, then epsilon can be just 11.7 epsilon naught. And also x is larger than half a and smaller than just a, then our epsilon becomes 3.9 epsilon naught. So in these cases, actually this epsilon can be still pulled out. It becomes just a Laplace equation. However, we cannot apply this condition when we have x equal to just half. In this case, epsilon is no longer a constant over the position, so we have to consider the variation of epsilon for this right problem. So instead of changing it to Laplace equation, we have to keep the original form. Of course, in this lecture, we are considering source-free case, so rho can be safely regarded as 0. How can we solve this problem, the right problem? That is discussed in the next slide. Let's rewrite the form once again. Epsilon, this is x-dependent one, and d phi dx equal to 0. So how can we solve this problem? In this case, we will introduce such a technique. So here we have equation. This is written in the differential form. Then we will make the integration of this equation over certain range. Let's say that there is a certain lower bound and upper bound of our integration. And now we wanted to make the integration of equation itself. So then this is just integrated left hand side. Then what will happen to the integrated right hand side? Since the right hand side was 0 identically, so even after performing the integration, our right hand side should be again just 0. Let's go to the next step. Since we are performing the integration, and since the integrand is already differentiated with respect to x, this integration just to recover the terms like this. So we will have the form like this: epsilon x d phi over dx, and we will take the difference in a upper bound and lower bound. That will be the result of our integration. Simply speaking, the term epsilon multiplied by d phi over dx evaluated at upper bound and lower bound are calculated, and their differences are needed. So let me write down once again more explicitly. So we have to calculated at upper bound minus epsilon x d phi dx at lower bound should be 0. So if we have the equality here, the first equation, then later we will have again the equality and equality and equality. So since the differential form is satisfied, even after we take the integration, the integrated term should be also valid. So now our goal is just to discretize this integrated term instead of this differential term. The natural question is, then how can we decide this upper part and lower part? what is the valid values for upper bound and lower bound. So if we are considering the Poisson equation around x equal to xi, the ith point, then the upper part is typically set to be xi plus 0.5, and lower bound is also set to be xi minus 0.5. Do you remember the meaning of x sub I plus half and x sub I minus half in our notation? It was defined as just a midpoint between xi and xi plus 1 and xi and xi minus 1. So I'm now suggesting that by setting the upper bound and lower bound as xi plus half and xi minus half respectively, xi plus 1 and xi minus 1, I'm suggesting the integration from this lower bound to this upper bound. So this is the range of our integration. So why do we set the upper bound and lower bounds in this way? It is because in this range, the nearest grid point is xi. By considering the nearest grid point, we can make this lower bound and upper bound. Now we assume that this upper is xi plus half and lower is xi minus half. Then this integrated form now becomes d phi dx evaluated at x sub I plus half and epsilon at this point minus now epsilon d phi over dx evaluated at xi minus half, and epsilon also should be regarded as the epsilon at this point. Here, the epsilon written in this position should be interpreted as the epsilon at xi plus half. Therefore, now we can introduce certain differences. Now this epsilon should be the epsilon at I plus half, and this is corresponding to I minus half. If we have several positions, and let's assume that this is the interface between two different materials. For example, left hand side we have silicon and right hand side we have silicon dioxide. In this case, what is permittivity for this point? What is permittivity? What is permittivity? We can certainly say this is corresponding to 11.7 epsilon naught, also 11.7 epsilon naught, and 11.7 epsilon naught, because they are belonging the silicon range. Also, in the case of silicon dioxide positions, then we can say this is corresponding to 3.9 epsilon naught. Also, this one is corresponding to 3.9 epsilon naught. Then what is the permittivity at this interface position? Is it 11.7 or 3.9 or just half and half? So average of 11.7 plus 3.9. So we have no idea about the exact value at this position, because this position is belonging to silicon and silicon dioxide same time. So we cannot answer to this question. But let me ask you one other question. How about the permittivity at this half-indexed position? And how about the permittivity another half-indexed position? Although this point is quite close to the interface, but still in this case we can surely say 11.7 is the relative permittivity. Also for this half-index point, we can certainly say 3.9 is relative permittivity. So if we adopt this picture, then we have great advantages. The epsilon and here epsilon no longer ambiguous. Depending on the material system, for these 2 points are belonging, I plus half or I minus half, we can certainly determine whether this is silicon or silicon dioxide, because such kind of ambiguity only occurs at the interface position, and interface position is integer indexed position. So this half indexed position never suffer from the ambiguity. Let me summarize. Simply speaking, we are working with the integrated form of our generalized Poisson equation. Instead of directly discretizing this second order differential equation, we just take the integrated form, and after that, by discretizing these two terms obtained from at upper bound and lower bound, we can simply evaluate this term without any ambiguity. For example, let's go to n equal to 5 case. Then let's say we have just 5 points, 1, 2, 3, 4, 5, and x1 we have a directly bounded condition, and x5 we have also another directly bounded condition. So for our system, we have the first row and the fifth row, the last one, corresponding to just diagonal component whose value is 1, and all other components are just 0. And here we have also right hand side of our AX equal to B system, and here we have 0. This 0 is corresponding to our 0 volt. And here we have 1. This is corresponding to the applied voltage 1 volt. If we apply 2 volt to the right contact, then we will have 2. If we apply minus 1 volt to left contact, then we will have minus 1. So these two laws can be easily evaluated. There is no difference between Laplace equation and Poisson equation in this boundary condition. But please have a look at the internal point. So in our case, second row, third row, and fourth row are corresponding to internal points. In this case, we have to evaluate the integrated form of our Poisson equation. Then, what will happen? For this x equal to, we have to consider the position like x 1.5 and also x 2.5. In this case, what is it? This point is belonging to just silicon, and x 2.5 still belonging to silicon. So we will use just 11.7 epsilon naught and 11.7 epsilon naught for our permittivity. We can say the upper and lower at upper bound and lower bound, it becomes 11.7 epsilon naught and d phi dx evaluated at x 2.5 minus 11.7 epsilon naught d phi over dx evaluated at x 1.5 equal to 0. And since this epsilon naught is shared by these two terms, the first term and second term, we can easily eliminate it. Okay, so we have just eliminated, and now we have to introduce the discretized form of our first derivative defined at x sub 2.5. How can you do that? We just did it before. Delta x phi at 3 minus phi at 2. That's it. And 11.7 phi 2 minus phi 1 divided by delta x. That is the discretized form of our Poisson equation evaluated at x2. Then by multiplying delta x to the left hand side and right hand side, and we will get something like this: 11.7 phi 3 minus 2 times 11.7 phi 2 plus 11.7 phi 1 becomes 0. This is scaled version of our Poisson equation evaluated at x sub 2. Then let's repeat it once again for our interface node. Interface node here means x3 node. In this case, the lower bound becomes 2.5 and upper bound becomes x sub 3.5. We can say this is corresponding to 3.9 epsilon 0. So everything is quite similar, but we have to make some differences. Here, instead of 2.5 and 1.5, now we have x sub 3.5 and x sub 2.5. Still, we have silicon in this lower bound, but upper bound, instead of 11.7, now we have 3.9. So the next equation also have just 3.9, and now we have 4 phi 4 minus phi 3, phi 3 minus phi 2. Then the final equation now looks like this. Instead of 11.7 for certain positions. Now we have 3.9. For example, in this coefficient for phi, sorry about that, here we have phi 4, phi 3, and phi 2, and 3.9 plus 11.7 appears as a coefficient of phi 3. So, simply speaking, now we can come back to our slide, and here you can see that this is the matrix for our Poisson equation. So please have a look at this second row and fourth row. In this case, we have same permittivity for upper bound and lower bound. Therefore, at the center node, we have the just doubled relative permittivity. Also, in X4, we have epsilon 2, epsilon 2. So therefore, 2 times epsilon 2 occurs in the diagonal component. And also, just scaling it, they just becomes 1 minus 2, 1. So this is just as before. The only difference occurs at the third row. Third row corresponding to the interface, and here we have the relative permittivity for lower bound and relative permittivity for upper bound, and as a diagonal component we have the sum of epsilon 1 and epsilon 2 and minus. So this one makes certain difference in our equation. So why don't you just do the simulation together with me? Here we have a MATLAB script already written, but let me just do it together with you. Okay. Our goal is to make A matrix and B vector and solve it to get the solution phi. So B is simply given by zeros 5, 1. And its fifth component becomes 1. Okay, we have prepared B. And how about A? Then A should be a square matrix whose size is 5 by 5. So we have just a null matrix, and A's 1, 1 component should be 1, specifying the boundary condition. Also 5, 5 should be 1, also corresponding to the boundary condition of the right contact. And now we are filling the internal nodes. For example, 2, 1 is corresponding to 11.7, and 2.2 is 2 times 11.7. Finally, 2, 3 is corresponding to 11.7. So now we have the A matrix whose second row is correctly evaluated. Then how about going to the fourth one, 4, 3 and 4, 4 and 4, 5, corresponding to just silicon dioxide. in this case, still we have homogeneous permittivity for every node. So 3.9, 3.9. Okay, as you can see, here we have just 3.9 and it's doubled values and 3.9. Oh, I made a mistake here. We have to have negative sign for this and also negative sign for this. Oh, I made a really big mistake here. We have to have a minus and minus sign. So our ratio should be 1 minus 2, 1, 1, minus 2, 1. If you introduce 1, 2, 1, that will really change the behavior of your system. So please don't make a mistakes just like me. And let's go to the most important line. 3, 2 and 3, 3 and 3, 4. In this case, now we have 11.7 for silicon area and here 3.9 for silicon dioxide layer, and at the center position, sum of 11.7 plus 3.9. Okay, now we have completed the construction of matrix A. So when we compared the Laplace equation, what is the difference? Actually, this one and second row or fourth row and fifth row are all the same with the Laplace equation, because although we have different numbers, they can be easily scaled to 1 minus 2, 1. Also, fourth row can be scaled to 1 minus 2, 1. But the third row is nothing related to 1 minus 2 ratio of the Laplace equation, so nothing will be the same with the Laplace equation. Then why don't we calculate just the phi function? So phi written x here, now given by this simple operation. Now we will get the x which is satisfy a times x equal to b. Then when you enter, oh, now you can see that it is 0 and 0.125 and a half and 0.625 and 1. So at the center point, what is the value? This is a quarter. So let me just draw it graphically. By solving this example, then we have achieved this result. Say this is 0 and this is A, and at left contact, at left contact we have number 0 and x equal to A, we have number 1. 1 is corresponding to 1 volt, and we have midpoint corresponding to 2A, and its value was a quarter. So this is a half and this is a quarter. So now we have the value here. It simply becomes a straight line and a straight line. This is the result for solving the system where we have silicon half and oxide half. What will happen if we have really silicon only or oxide only? Then certainly our function will look like a straight line over entire range. You can easily check it by changing the coefficient inside your A matrix. I strongly recommend you to just insert 11.7 for all cases, like 11.7, and this one becomes just minus 23.4 and minus 23.4. Then you will get exactly straight line over entire domain. It is up to you, and please do your exercise. Okay, so I think that's it for our lecture number 4, and the homework is given to you. Now consider more realistic case. In the lecture, we have considered a simple system where half silicon and half silicon dioxide, but in this homework problem, we are now considering more realistic case. Here we have two different materials. First, silicon dioxide, and second, hafnium dioxide. Silicon dioxide has the thickness of 0.5 nanometer, and hafnium oxide layer has the thickness of 1.9 nanometer. These are all technically relevant values, and its relative permittivity is 3.9 for silicon dioxide, and the high K material, hafnium oxide, its relative permittivity is 22. So please neglect mobile carriers. We have not discussed it in the lecture, so simply just neglect it, and please try to calculate the capacitance per area. And when you make your potential distribution, from the potential distribution, you can calculate the value of D vector over its x directional component, and from this D, and from applied your bias voltage 1 volt, you can calculate the capacitance per area, and you have the analytic expression for it, from which can be easily calculated from these conditions. And in your report, please make a comparison between your numerical result and analytic solution. Okay, this is all for lecture 4 and homework number 4. So see you next Monday. Bye.